So before I move on, I just want to clarify something that I misspoke about at the very end of the last video. I said that SO2 was only LDF. It is polar when you do out the Lewis structure, so it's actually LDF and dipole-dipole. But it doesn't matter because Ki is still ionic, so Ki still has the highest boiling point. I just wanted to clarify that before I moved on. So now I'd like you to practice this. Okay, so I know you just started this video, but you can pause this video and rank them from lowest to highest. So lowest would be number 1, the middle one would be number 2, and the highest one would be number 3. All right, so hopefully what you did was wrote down what IMF these are going to have. Okay, so to start, you can do LDF for all of them, or you can do metals and non-metals. So this one is going to be a metal, and this one is a non-metal. This is a non-metal, 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 and non-metal, non-metal. Okay, so that gives us, for this one, is ionic compound. So it has LDF and ionic forces. This one has LDF, obviously, and then it is a covalent molecule, which means we now need to decide whether it is polar or non-polar. So if you do out the Lewis structure for this one, it does have 4 sides, but since one of those sides is Cl, it is not completely symmetrical, and that means it does have dipole-dipole. It does not have hydrogen bonding, however. Even though it does have a hydrogen, it needs to have oxygen, fluorine, or nitrogen. And since that doesn't have those, there is no hydrogen bonding here. And then here we have another covalent compound. And this one is nonpolar, so we do not put dipole-dipole. It's just LDF. Now, also it has no hydrogen bonding for 2 reasons. One, although it has a hydrogen, it does not have nitrogen, oxygen, or fluorine. And 2, it's not polar. In order for it to have hydrogen bonding, it needs to be polar. All right, so then you can just go ahead and rank them. Remember I said 1 is the lowest, so that's going to be this one because it just has LDF, which is the weakest force. 2 would be right here because dipole-dipole is slightly stronger than LDF. And 3 would be right here. So now I want to go back to something I said in the first video, which was there's going to be one molecule that the Lewis structure looks like it's nonpolar, but I need you to know that it is polar, and that is water. So when you do the Lewis structure for water, it comes out like this. But if you learned molecular geometry or you watched that extra video that I posted, you would see that even though it looks symmetrical, because the top and bottom is the same and the left and right is the same, it's not actually. When you do the shape of water, it comes out to be bent. Okay, so this is the shape of water. And you might remember that from your biology class. Whenever water is drawn in biology, it's drawn like this. And without getting into too many details, because you can watch that video, it's because the 2 lone pairs are like this, and because of valence shell electron pair repulsion, these electrons try to get as far away from each other as possible, and it ends up with this shape. So again, if you do want to know more about that, there is a video posted for you. But the basic idea is the electrons repel, so we end up with a bent shape. And as you can see, this is not symmetrical. So that means that this has dipole-dipole forces. It also has hydrogen bonding because there's hydrogen and there's oxygen. In a water molecule, the oxygen is going to be slightly negative and the hydrogens are slightly positive, both of them. So if you had another water molecule, they would be attracted. The oxygens would be attracted to the hydrogens and vice versa. Okay? Now, the reason we need you to know about this is because water is just everywhere. And so it ends up being very important to the way our world functions, okay? Water has very strong hydrogen bonding. For that reason, there is a lot of stuff that you studied in biology that's explained by the geometry and polarity of water. So for example, surface tension. So one of the things that's always in every biology textbook is a bug walking on the surface of water. And I think that's in one of the activities that you're going to do after these notes. Something about that. The reason for that is because of surface tension. Now, because of this hydrogen bonding, it's almost like water molecules are sticky because they're attracted to each other so much. So something light, like a bug, can walk across the surface of the water because it's almost like water has this little film on top of it. Now, obviously, we can't because we would break the surface tension. We break that IMF, even how strong it is. But things like bugs can do that. Capillary action. You might remember photosynthesis from biology. You would water a plant or a tree or something on the bottom where the roots are, but the whole entire plant needs to have that water. It travels up through something called capillary action. That is because of the hydrogen bonding. It sticks to the surface of the different things inside the plant and it goes all the way up to the top of it. Now, density is another thing. Now, density, you know that solids in general are more dense than liquids, but ice floats in water. And that means that ice must be less dense than water. And that is true. Okay, so for H2O, the solid form is less dense than the liquid form because of hydrogen bonding. It kind of, the repelling of the different and the shape is going to make the molecules spread out a little bit more. And then this one goes with what we just studied. The boiling point of water is much higher, and the melting point is much higher than the boiling points of H2S, H2SE, and H2TE. The reason I gave you these three examples is because that's the ones that are in the same group as oxygen. So oxygen, sulfur, selenium, tellurium. So you would expect them to be similar, but oxygen is, hydrogen with oxygen, so water, is much higher because of the hydrogen bonding, because the other ones are all going to be polar, but not have hydrogen bonding. So they'll have dipole-dipole and not hydrogen bonding. Okay? So the other concept that goes with water is the concept of like dissolves like, and that's going to be in one of the activities that you do. Like dissolves like, that principle means that polar things dissolve other polar things. Non-polar things dissolve non-polar things. So water is a polar substance. So that means the things that would dissolve in water are also polar. Okay? The big thing in the real world that you need to know that is non-polar is oil. Oil is non-polar. So in one of the activities, you're going to talk about why do you use soap? Because a lot of the stains that people get have oil in them. And so that means those stains are non-polar. So just using water wouldn't dissolve them or get rid of it. So you need something else. And so that's one of the simulations talks about soap and how that helps when you have a lot of different stains. Like grease has a lot of oil in it, stuff like that. Okay, so that's it for the videos. Like I said in the first one, we have office hours on Wednesdays. We're also all pretty available. So if you need any help understanding any of this, or as you go through the activities, they don't make any sense to you, just let us know. We are happy to help.